In the last lecture, we have discussed the linear regression. What we have seen that in the cost function of the linear regression, which is essentially a convex paraboloid, we have to find the local or global minimum. We started anywhere and we have to reach the global minimum. Now we need an algorithm, and by virtue of this algorithm we can reach the global minimum. So in this lecture we are going to introduce such algorithm called gradient descent. So in this lecture, first we define gradient descent, and then how gradient descent algorithm is applied on the linear regression to find the global minimum. Then we go to the multivariate linear regression, and then two variant of the gradient descent algorithm, namely stochastic gradient descent and minimized gradient descent. In the last class, we have discussed about linear regression. The main problem of linear regression was that we are given some data points like this. These are the annotated data points or supervised data points, and what we have to do, we have to hypothesize a line, straight line, so that this straight line will represents that these data points. What was our goal? That given any x, that we project on this line so that we can get this corresponding y value, and that was the basic problem or basic agenda of linear regression. Now how are we going to find this line? So the cost or the error between these data points and the corresponding points in the line should be minimized. So for that reason we define a cost function, that is the parametric form of this cost function is j of phi 0 phi 1, where this error term means, let this particular point, this is the actual point and this is the predicted point, means this. So we calculate this difference h phi xi minus yi, take it square and sum it over for all the data points. Let there is m data point, so sum it over 1 data points and average it out. So this is the square function and this is the cost function of this. And if we plot this cost function, we can get such this convex paraboloid. Now the idea is that we have to find out that this local or minima of this, or you can say the global minima of this surface. Since it's a convex surface, our local and global minima are same. So we starting from any point such that this is a corresponding this line, and again we update this phi 0 phi 1 so that we slowly coming down to this global minima, and it is a corresponding contour plot. It's a cross sectional of this, and similarly we can reach this to the global minima. Now the question like how we traverse from here to here to here. So from this traversal, for this traversal we are going to introduce an algorithm that is called gradient descent. So gradient descent is an optimization algorithm which is used to minimize a function. Function means this kind of a, here the work cost function, by iteratively moving direction to the steepest decrease. Steepest decrease means that it's an towards a negative gradient. Okay, so in the gradient descent is usually finds the local optima, as we have seen here that we try to find the local optima. Since it's a convex, is the global optima, same thing. So we try to find given this kind of surface, we gradient descent, we try to find the global optima. Here the global and local is same, and for a differentiable function, see that our cost function is differentiable. Okay, so it take the steps in the direction that reduce the function that we have seen. But to understand this, we take a function, it's a univariate function. Although it was in our linear regression case, it's a bivariate function. For just simplicity of understanding, we take this a univariate function, f of alpha, which is differentiable with alpha and convex in nature. Now, this alpha k plus 1 is basically a parameter, and how parameters are updated, it is in this equation. Now, alpha k is minus, this is called the learning rate, gamma, into this is the d of d alpha k of this function f of alpha k. So this is the your cost function. It is differentiable at alpha k and in multiplied with this learning rate, and this total thing being subtracted from the initial alpha k or current alpha k to get back the next alpha k plus 1. So this is a parameter update or weight update, once we can say step. Now if we try to visualize that what is actually happening here, you can see here this is the alpha k, and we can find this slope kind of thing here, and we multiply with gamma, so that we can here this slope is basically this direction, so we can from this alpha axis from alpha k plus. One interesting thing is to be noted here, that this alpha k plus 1 is towards the f minima, that is our local minima or global minima, since it's a convex surface. So this is basically an iterative function, so that by this kind of iteration, we can slowly we can from here to here to here find this. So alpha is reducing, thus alpha f of alpha is approaching to the f of min, which is the local minima, and this gamma is the learning rate. It controls how big steps we are taking over the gradient descent. We'll come later about this gamma. Okay. Now, when we apply this our gradient descent algorithm for the linear regression, our cost function was j of 5051, as we said earlier. So 1 by 2m, it's sum it up over h5 xi by h5 xi minus yi square, and sum it over this m and average it out. Now this cost function, as we seen earlier, that is convex paraboloid. So what we are basically trying to do, from any point from here to any random point, we are trying to find the local minimum. So since it's a convex, it's a global. Now as this error surface is convex, local minima, global minima is same, as you already said. So if I go starting from anywhere in this error surface, if we can reach this global minima, so that our square error will be minimized, and that is why what is our requirement, so that if this error is minimized, we get a line corresponding this 5051, that it the most well represents the data points. That is actually what we want. So that is the basic understanding that we tried. That's why we try to find the minimal square error, and so that indicating the best fit line. And by the virtue of this gradient descent, which is iterative optimization algorithm, starting from anywhere in this error surface, and it traverses to the local minima or global minima of this convex surface. So this is the main idea of gradient descent for the linear regression. Now we formalize this descent algorithm in mathematical form. As we know, this is our cost function 0, 5, 1, and what we have to find, that we have to find such theta phi 0, phi 1 so that we can minimize this j of phi 0, phi 1. So this function. Okay, so we start from any arbitrary, as we said here, that we start with any arbitrary point here. We started from here, we can say anywhere, and slowly we come to the global minima. So let, if it's phi 0, phi 1, 0, phi 0 is equal to 0, phi 1, maybe, and we keep on changing phi 0, phi 1 to reduce this function j of phi 0, phi 1, and sometimes it's the global minima. So how we'll keep changing? Using this equation. Okay, that particular equation is, we are changing this alpha k, and there this is alpha k, since it is univariate, now it is phi 0, phi 1. Okay, so with this background, we try to define our gradient descent for linear regression problem. This is our cost function, as we have mentioned. And then this weight updation, there is two parameters now, the two weights, that is phi 0 and phi 1. Phi 0 is basically updated by this phi 0 minus this gamma, this learning rate, then del of del phi 0 of j of phi 0, phi 1. So this is basically differentiate with this with respect to the phi 0, multiplied with this learning rate, and so it is subtracted from the phi 0 to get the new phi 0. Similar for phi 1 of the same thing. So in this way we can get the weight updation or parameter updation algorithm, and in every iteration we can get a new phi 0, phi 1, so that we can better and better line to fit our data points. So if we write this gradient descent algorithm, that is L'Hopital convergence. Convergence means we get the local minima, so that phi k in phi k minus sigma gamma to del of del phi k to j of phi 0, phi 1 k 0. Since there is only two parameters, this k 0 to 1, where this gamma is learning rate. Okay, so this learning rate controls how bigger steps to take over the gradient descent. So how quickly we can get the global minima. Now, what is the visualization of gradient descent algorithm on the linear regression? As we have mentioned, this is the algorithm. Repeat until the convergence. Phi k is equal to phi k minus gamma into del of del k, del phi k of this cost function j phi 0, phi 1. And this case is 2, phi 0 and phi 1, so it is a 0 to 1, where this gamma is learning rate. Now, what exactly this means? We starting from any point, any arbitrary point, and then keep on changing this, that for this is maybe phi k, k1 and k2 and so on, we can get this. So here you can say that our updation algorithm work in this scenario or in this format, and we can, from starting from here, the first step we can get here, and then this position here. In the corresponding contour plot, that we can start here, from corresponding first come here, and then this is the, so we are keep on updating this phi 0, phi 1, so that we can, this error is minimized, because that is the meaning. If we can get the lower position or the minimum position of this error surface, that means error is minimized. And if error is minimized, we can get the line which produce the least number of errors. So that's why we can get the line which best represents our data points, and that is our goal. So that we can say this is the visualization, that how gradient descent to help linear regression to get such best fit line. Okay. Now, can we say that given this setup, this gradient descent setup for this linear regression algorithm, can we ensure that this will converge, always converge? Now what we understand that our cost function is a convex function. Now we again take a univariate cost function that is convex in nature to just understand. And what we have to do, the goal is same. We have to find such phi 1 that will minimize this phi 1. Okay. So in this case, weight updation and gradient descent is basically this. Phi 1 is equal to phi 1 minus this gamma into del phi 1 j power phi 1. That is exactly the same algorithm. Here you can see if your slope is positive, that means it is in this part, this side. Now this thing, if it is a positive, that means this part is positive and this gamma is also positive. So whole term is positive term, and if it is minus, it is subtracted from phi 1. So phi 1 is basically reduced. And it is interesting to see that this phi 1 is in this axis. So if we have to come to the global minima, phi 1 should be reduced. And since it is in a positive slope, this phi 1 is reduced so that we can slowly reach to the global minima. Now in another case, if the slope is negative, that means this is negative, this part, and this is positive, so it is total negative term, and so it become a positive. Then this minus to minus is positive. So then phi 1 is equal to phi 1 plus this value. So now it is in this portion and position, and this phi 1 is getting increased so that it slowly go to this global minima. So what we can observe in this diagram, that even if slope is negative or positive, so in any portion of this error surface, it is updated such a fashion, it slowly converges or slowly reach the global minimum. So now we can conclude from this illustration that whatever the initial values of phi 1, this gradient descent will ultimately reach the global minima and thus converge. Okay. So this is the proof of convergence of this gradient descent if the error surface is convex. Now this what we have understood about this learning rate. As we said earlier, learning rate is basically that how big steps we are going to make in this path of convergence. Now let's try to understand the implication of this gamma, that if gamma is very small, now you can see the gamma is very small, the iterative pathway, this path is very small, so it's very slowly, every path is very slow, very small, so it's very slowly coming to the global minimum. So what we can say, the learning rate is too small, the rate of convergence becomes slow. It will come steadily, but the rate of convergence becomes slow. On the other hand, if this gamma is very high, is too big, then there is a chance it just jump over the global minimum. So in this way, this way, this way, this way, and it just jumping over and there, and it may not converge, never. It's never converge. So what we have understood from there, the learning rate should be in between, so that it not should be too small and it should not be too big, so that it converge in a kind of subsequent or optimal rate, and not too big, it is just over and over, just jumping over this global minimum. So that we have to choose this learning rate such way so that we can reach the global minima in a very optimal time. As of now, what we have discussed, that our linear regression is univariate linear regression. Then the input variable x is single dimension. Now we go for multivariate. That means our linear regression is more than one variable. But before that, we discuss multivariate linear regression. We want to understand what is the input space and what is the feature space. Now our input is an image or anything. So this input is now this data points is our one input. If it is an image, let's say as an example, this image is your input. Now this image is not fed to your classifier. Rather, there is a features that has been extracted from this image. Generally, this feature space may be single dimensional, may be multi-dimensional. For this, here this feature space is k-dimensional. So this feature space is phi 1, phi 2, phi 3 up to phi k. This number of features. It may be some values. So it is a real values, anything. So there is a difference between input space and feature space. That means the input space, this is called in machine learning terminology that feature extraction. Okay, that we'll see later in lectures. So the main thing that we have tried to understand here, that input space is converted to the feature space and these features had been given to the classifier. It's a linear regression, classification, whatever. Regression, classification. Now here you can say this is a three-dimensional space and this is the point. That means this point in three axis there is some values, and then this axis p where k is equal to 3. This is just a three-dimensional visualization. So it is very tough to draw the more than three-dimensional, though that's why we just draw the three-dimensional one. But it may be any dimension. Okay. Now, with this background, we try to understand that multivariate linear regression. So far as we said that we use the univariate linear regression. So feature space is single dimensional. Fine. Now this single dimension, now our hypothesis function, that is h phi x, is a straight line, and the parametric form is a straight line from y is equal to mx plus. So in our linear regression is a phi 1 x plus phi 0. This is for m1, this is for m0, and c, that is the basic thing. Now for our multivariate case where the feature dimension is k, this hypothesis function is become this phi 0 plus phi 1 x1, phi 2 x2 dot 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 phi k xk. So this phi h is hypothesis function is now. This is the only difference. Is the univariate case to the multivariate k-dimensional space. If you write in a bit matrix format, so it is h equal to phi of transpose and x. This is x vector now. What is the phi look like? It is basically this phi 0 to phi k. So it's a k plus 1 dimensional because this phi 0. Same this phi 0, this phi 0. And x, where x0 is equal to 1, it is basically k plus. This is also similar dimension. So that we can write in this matrix format that phi 0, phi 1, phi 2, phi k, and x0, x1, x2, xk. This transport for this multiplication. So ultimately what we can understand that our hypothesis function h equal to phi transpose x bar or x. This is our multivariate linear regression hypothesis function. Rest understanding is. Now as we see that our hypothesis function is this, our cost function is this, because cost function now only difference is that our this was initially this is single dimensional, now it's a k dimensional. Okay, other things is basically same, it 1 by 2m I is equal to 1 to m, where m is the number of samples, and h phi of xi minus yi, that's squared term. Each this we can get this. Now this phi, but one thing, this thing is now multidimensional. That we have to understand. Okay. Now, if we use this gradient descent for multivariate regression, our term is becoming this, that phi I is equal to phi minus gamma phi of theta of del phi I and j of phi 0 phi 1 phi k, where this gamma is lying. Okay. Now here we understand, we repeat again when our univariate case, this phi 0 is equal to phi 0 to gamma into this. This is the basically the differential of this cost function. If you take the difference, this is your differential, and for phi 1, this is the differential is x1. This is because again this x0 is 1, so it will write 1. But this gamma is landing. Only difference here that this is for phi k, because our cost function up now phi 0 phi 1 to phi k, and this phi 0 any parameter phi j, this to gamma into 1 minus m 1 by m to 1 to m to this up to m, we have to this square term. This is the differential. Okay, so where j is equal to j to k, because this means this is dimensionality, that this is a our initially it was single dimension 0 to 1, now 0 to k. So phi 0 is equal to phi 0 minus this term, this is the differential of x01, this is phi 01, the same thing is x1i and so on, and phi k is equal to this. So what is the basic understanding? The things are very similar, only the dimensionality change from this was the single dimensional, where cost function is bivariate, it is a multidimensional or k dimensional, this cost function k plus 1 variate. That is the main difference. Okay. So what we have seen, by the gradient descent algorithm, we can find the local optima or local minima for the error surface. Now with this typical gradient descent optimization, there are some problem. To understand the problem, we have to first understand this equation. This equation is typically a weight ablation equation we have discussed in earlier slides, that this phi j n is equal to phi j minus this is landing rate gamma, and this is basically the error term, that h of phi xi and so it's y of phi, and it is, since it is differentiated is in of phi j, so it become xji, so it is a differential function, and this is 1 by k, so this is the, but the major thing that we have to understand, these values is sum it up over all the data samples. So in typical gradient descent algorithm, what is basically called the full batch gradient descent, what we are going to do, we sum it up the whole data set. So whole data set means total number of data points what is present in them. Now there is a certain advantage and disadvantage. What is the advantage? Since we take every samples in consideration, that when we are getting the minima, that path of convergence is less noisy, or we can say less random manner, it is more straightforward. But if the data set is very big, now this M is very high, let's say if it is a million samples, then this computation for a particular iteration, now we'll say this iteration epoch kind of, iteration. For every iteration, these values computed million times for a single web updation, and that is very computationally expensive. So that is the one of the major bottleneck of this full batch gradient descent, where we take all the data points in the data set. That means this m, every m we taken care of. So this makes this particular algorithm very much computationally expensive. Okay, so that is the typical problem of this gradient descent. To mitigate this problem, what we basically do, that is called stochastic gradient descent. Now this stochastic term is coming because there is somewhere some randomness is being added to this process. We'll see how this will come. Now in this stochastic gradient descent, or generally we call the SGD, what we'll do, we'll take a single sample rather than full data set. We choose a single sample. Now there's a question of choosing. That choosing is a random choice. That's why it is called stochastic. We stochastically or randomly choose the single sample out of the full batch. So among the all m's, whatever big this m is, we take a single sample. So we can say here our batch size is 1 to perform the each iteration. Now this sample is randomly shuffled and selected for performing the iteration, and thus introduce this stochasticity. Now you can say this particular formula now becoming this. Now here there is no sum it up over 1 to m, rather only a single sample I has been chosen. And this choice, if this choice is represent the data set well, then this thing will work well. But still it is a random, and that's why it's called the stochastic gradient descent. What is the advantage? Advantage is that the complexity, this time complexity or computational complexity, become very less, because it is m is total number of samples. If it is a very big, and but we are taking only one sample. Okay, so in stochastic gradient descent, when we compare with this typical batch gradient, full batch gradient descent, now this is less expensive of this full batch gradient descent, because we take only one sample instead of sum of gradient of the cost function of all examples. But there is a issue. Since we are taking only one sample, this data set, from this data set, and it is chosen randomly, so the path of convergence looks a bit noisy or a bit random when we are from anywhere. If we go to this local optima, this path of convergence may not be very straightforward like this full batch gradient descent or typical gradient descent in case of stochastic gradient descent. So the path taken by the algorithm to reach the minima is usually noisier or more random than your typical gradient descent algorithm. But as a whole, because in SGD, since only one sample is taken consideration, specifically when the data set is very high, then if it is a order of million or 10 million something, it's a very big data set, then this, even if it is a random, the path of convergence, the time has been reduced substantially. So it doesn't matter as long as we reach a minima and with a significantly shorter training time. Even if it is a random, but still the much shorter time we reach the training minima at the training time. And that is the advantage of stochastic gradient descent. Okay. Now there is another variant of gradient descent that is in between. In between means this is a too extreme case. Let there is a very big data set. Data set is order of million, and there is another version is stochastic. Only one sample is being taken. But in between, if this sample size, that number of data to be considered in per epoch or per iteration to get a update or updation, that in between, that p is less than is equal to m but greater than 1. Okay, so this p we choose very judicially. Then this variant is called mini batch. That means a batch with less number of samples from the whole sample. So it is less than is equal to m. Okay, so this approach, this is definitely computationally efficient than the full batch, and again the path of convergence is less noisy than the stochastic gradient descent. So two advantage of two extreme cases are taking consideration in this mini batch, and most of the cases, in practical cases, we use this mini batch. Now the thing is that it is the equation of the weight updation become, now it is 1 to p. Now this p is the number of sample in this mini batch. Okay, and when p is equal to 1, which is a stochastic gradient descent. When p is equal to m, it is called full batch gradient descent. And but this p is basically in between m and 1, and it has been judicially selected so that we can a balance between computational efficiency and the randomness of the paths of convergence. It's called mini batch gradient. Now if you see here that this path of convergence of the full batch, you can say that this path of convergence is very straightforward. So almost there is no randomness involved here. It's very straightforward from anywhere to from this error surface to the local optimum. Now before the stochastic gradient, it is much random. This is two extreme cases, but you can see in mini batch this is random, but still it is much less random than stochastic gradient descent, and this time complexity is much lower than this full batch. Definitely that randomness is slightly higher than full batch, but this is the so computation complexity is less than full batch, also having path of convergence is less noisy than this. So what we have seen here, that we choose this p in such a way so we can get the advantage of full batch in respect to this randomness in the path of convergence and the time complexity of this SGD. We can get both the advantage and get a very optimal solution. So in summary, in this lecture what we have discussed, that we define gradient descent, and then we define or we can illustrate the gradient descent algorithm for linear regression. Then we discuss what is the multivariate linear regression on the basis of our univariate linear regression. Then we understood what is stochastic gradient descent and how mini batch gradient descent is. Then in next lecture what we will do, that logistic regression. Generally this is called classification. Okay, so we thank you very much.